Let's talk rockets. How does a rocket engine work, or any kind of engine that can get us to space or float around in space?
The basic principle is conservation of momentum. So you throw stuff out the back of the engine oops, and that pushes the rocket and the spacecraft in the other direction. So there are two main types of rocket propulsion. The one people are more familiar with is chemical because it's loud and there's fire. And that's what's used for launch and is more televised. So in those types of systems, you usually have a fuel and an oxidizer, and they react and combust and release stored chemical energy, and that energy heats the resultant gas, and that's funneled out the back through a nozzle directed out the back, and then that momentum exchange pushes the spacecraft forward.
Is there an interesting difference between liquid and solid fuel in those contexts?
They're both lumped in the same. So chemical just means that the release of energy from those bonds, essentially. So a solid fuel works the same way. And the other main category is electric propulsion. So instead of chemical energy, you're using electrical energy, usually from batteries or solar panels. And in this case, the stuff you're pushing out the back would be charged particles. So instead of combustion and heat, you end up with charged particles, and you force them out the back of the spacecraft using either an electrostatic field or electromagnetic. But it's the same momentum exchange and same idea, stuff out the back, and everything else goes forward.
Cool. So those are the big two categories. What's the difference maybe in like the challenges of each, the use cases of each, and how they're used today, the physics of each, and where they're used, all that kind of stuff. Anything interesting about the two categories that distinguishes them, besides the chemical one being the big sexy flames and
Fire.
fire? Yeah.
Chemical is very well understood. In its simplest form, it's like a firework. So it's been around since 400 BC or something like that. So that even the big engines are quite well understood. I think, one of the last gaps there is probably what exactly are the products of combustion. Our modeling abilities kind of fall apart there because it's hot and gases are moving, and you end up kind of, having to venture into lots of different interdisciplinary fields of science to try to solve that. And that's quite complex, but we have pretty good models for some of the more like emergent behaviors of that system anyways. But that's, I think, one of the last unsolved pieces. And really the kind of what people care about there is making it more fuel efficient. So the chemical stuff, you can get a lot of instantaneous thrust, but it's not very fuel efficient. It's much more fuel efficient to go with the electric type of propulsion. So that's where people spend a lot of their time, is trying to make that more efficient in terms of thrust per unit of fuel. And then there's always considerations like heating and cooling. It's very hot, which is good if it heats the gases, but bad if it melts the rocket and things like that. So there's always a lot of work on heating and cooling and the engine cycles and things like that. And then on electric propulsion, I find it like much more refreshingly poorly understood.
Lots more mysteries.
Yeah, I think so. One of the classes I took in college we spent 90% of the class on chemical propulsion, and then the last 10% on electric. And the professor said, like, we only sort of understand how it works, but it works kind of. And it's like, that's
what I'm gonna
interesting.
work on.
Yeah. And, even an ion engine, which is probably one of the most straightforward because it has just it's just an electrostatic engine. But it has this really awesome combination of like quantum mechanics and material science and fluid dynamics and electrostatics, and it's just very intriguing to me.